Welcome back. On this episode of Everything Embedded, we're continuing with our low EMI regulator series. In this episode, we're going to be doing the layout portion. The layout for a voltage regulator is absolutely critical. If you get the layout wrong, you'll have noise problems, stability problems, the noise will couple elsewhere into the circuit, and things are not going to work quite right. So this is a critical step. The key things we have to focus on with the regulators, there's a couple things that are called hot loops. And so these are areas where the current density is really high. So you have a lot of current that's switching fast going around these. And so the first one is the input voltage through ground around here. So we have these V in and the power ground. So as the switch turns on and off, this has a lot of current going through this capacitor. And there's this on this side as well. The other high current path is around the switch node. So we want to keep the switch node really small so that we don't have much parasitics. Otherwise, the switch node can radiate like an antenna into other circuits and into the surrounding environment. So in order to get the layout right, we need to start by getting the parts placement right. Laying out the traces is the easy part once you get everything laid out in a way that makes sense. So we'll want to make sure that we have all the parts near to where they need to be to make the routing and layout as simple as possible. To make seeing the layout a little easier, I've gone back to the schematic and added some net labels. So I added a V out label, a switch label, and then a V in label. This will help us to keep track of the traces once we're in layout and make finding the nets a little easier. So I'm going to save that. Now we can see on our pads here, things are labeled. So we have the V in pads, ground, we have the switch node, and V out is labeled over here. To make things a little easier while I route, I've turned off the fab and silkscreen layers just to help see the pads a little better. I also don't want to be clicking on things I don't want to be moving, so I've turned off some of the things in the selection filter. The other thing we can do to make these easier to see is assign some different colors to the nets. So for our V in net, I can go into the nets panel here, and usually for V in I'll use kind of an orange color, and then for my V out I'll use a more red color. And so that now highlights the rat's nest, and then that'll highlight the traces in that color as well. So now that we're set up, we can start moving our parts around. So this being one of the input capacitors, it's important that this one ends up right next to the in and ground pins. This is the other one. This is going to be a pretty symmetrical layout the way this part's set up. I did forget one other color. I'd also like to set up ground as a green on here. So here we can tell this is that critical V in current loop I talked about. And so we're keeping it really small with this capacitor. So high frequency currents will only move over this little tiny loop, which will reduce how much they radiate. And then for the inductor, we want this to be as close as possible to the switch output. So this way we'll have a plane that we'll be able to put through here and capture the switch. Then we'll go place our output capacitors very near the V out here. So now I've placed these three output capacitors right here. So we'll be able to have a plane for the output here, and then these can tie right into these grounds that'll be nearby. At this point, I'm just grabbing all the other passives around and using the rat's nest to see where they need to go and putting them as close to the pins as possible. For this bootstrap capacitor, it's a little tricky because we need access to the switch node, but this part actually gives us access. We can poke it through here and come out over here, and then this can tie through this with the resistor for the bootstrap. Since we have these ceramic capacitors nearby the inputs, this large electrolytic capacitor, really it doesn't matter where it goes, it just needs to be on the board to provide us some bulk capacitance. For this design, this capacitor is a little too large. However, it's one I already had, so I'm using it. If I was doing this design on a board where I was actually space constrained, I would probably use a smaller tantalum or ceramic capacitor instead of a very large electrolytic, but these can be very cost effective if you're not very space limited. So that we can hook these banana jacks up using standard test connectors, we're going to use a 0.75 inch spacing between them, which is the standard that like most multimeter plugs will have on them. I'm going to go into inches and set my grid to be on a inch grid of 1/4 of an inch. And then we'll move the plugs until they're on the grid. I can then center the rest of the layout between the plugs. So with this, we've got a pretty good start. We may have to make a few tweaks to some of the parts over here as we get routing, but this should let us start routing. The first thing I will do is go add my board outline. So to do that, we will go onto the edge cuts layer and go draw a rectangle on it. The next thing we need to do is set up our board stackup. By default, KiCad only gives us the front copper and the back copper. To modify that, we go into File, Board Setup, and then we can go to Physical Stackup and select 4 layers. If you're doing a critical stackup board, you could go set all of your spacings and everything in here. We're just going to let the board shop choose that for us. A 4-layer board for a converter like this that we're trying to have really low EMI is pretty critical. A 2-layer board has too much spacing and we will have slots in our ground plane. We need a really good ground plane underneath our converter in order to keep all of the return currents under control. So first we're going to go on to layer 1 copper and we're going to go create a zone. So we'll click on the zone tool and then we're on layer 1 copper and we're going to select the ground net. The name of this will be the ground plane. We do not want thermal reliefs on this since it's an internal zone and we don't have any through-hole components. If you wanted just for through-hole components, you could do relief for plated through-holes, but we're not soldering to any of our through-holes. And then we can click around our outline. If we hit the B key, it'll fill in that zone for us. One other setting that I'll point out I already have set, I have the zone set to be somewhat transparent here in the object, so you can adjust this slider to control how transparent the zone is. This helps make it easier to kind of see where your zones are at without them getting in the way as much. I'm going to use layer 3 for our voltage planes. So on one half of the board we'll have V in on layer 3 and on the other half of the board we'll have V out. So on this side will be V in. We're on layer 3. It's going to be solid reliefs. So we're going to want our V in to go over, so we make sure we pick up all of the V in, and then we leave a little bit of a gap before we pick up where we'll have V out present on the board. But I will start all the way up in this corner, and then we can see we need to cover at least about to the edge of the IC so we can capture these capacitors for that. We'll close that one up and hit B to fill again. Finally, for the zones, we'll add V out. Same settings as before, and this one will cover the right half of the board. Now, even with those zones on the internal layers, in the areas where we have those high current loops, such as around our V in and our V out, we're still going to want to connect all of those together with larger planes. So for that, we'll go to our front copper and grab the zone tool just the same, and we'll start drawing a shape that gives us the V in that we need here. We'll extend it a little bit out beyond so that we have some space to put some vias down to those internal planes. It doesn't matter if our zone overlaps some of the other pads a little bit, the clearance settings will take care of it. The clearance for these zones looks a little large right now, so I'm going to go edit that zone and change the clearance down. We'll now go on the other side and create a similar zone for this side's V in. Next, we will create some ground zones to capture the ground pads on all these capacitors on both sides. We'll extend this one out a little ways as well, so we have room to put some vias on. KiCad here doesn't quite behave, and it's not leaving a gap between these zones like we need it to. And the way to set that is you change the priority. So if zones are of the same priority, unfortunately it doesn't change this, but if we increase the priority of the ground zone, then now it'll push away that V in zone and give us the clearance that we need. Next, we need a zone for our switch node. And I'm going to set the switch node to be a higher priority than the ground node. So that switch node is pushing the ground out just a little bit down here, and that'll give us a nice short low inductance path for our switch. Finally, for the zones, we're going to tie our V outs together with a zone. So next we're going to start adding vias to get these planes stitched together. So there's this freestanding via tool, and we can simply grab that and start adding vias in. And these will take the class of the zone that we're adding them onto here. At this point, we can see we've stitched all of our vias down from these planes so that we'll have nice low inductance paths from these outer planes down to the inner planes in the board. At this point, we can begin routing the feedback network and the other supporting pieces for this design. To make routing easier, I turn off my inner plane layers so we can see just the top side, and then we can just start routing traces. For routing, I typically shrink my grid down to a much smaller grid size of a couple mils. This spot's gotten a little tighter than I want coming through here, so I'm just going to scooch this piece over just a little bit. Can route this down here. When a route comes out a little messy like this, we can use the D key to drag the route and kind of clean up that trace. So this one I'm going to pull back down since it got scooched a little bit, and then that'll let us pull this one back down, and that cleans that up. Since this one's ground, we're going to tie this straight down to the ground plane underneath. And we'll put a ground via on this side as well. It's generally a bad idea to share ground vias, since the return currents can cause a voltage drop across the via that can interfere. So for each ground pad, I try to use give it its own via. This trace doesn't have a great way to come through, so we're going to put it on the back side. So we'll hit V, transfer over to the back side, and then we'll be able to put another via right in here, and then connect that up back on the top side. Same thing for this V out. It's a bit congested through here, so we're going to pop a via through. And run this V out signal on the backside. That will also make it easier because we need to connect that over to the V out over here. So we can drive this underneath here and connect it through to one of these vias. To hook up this capacitor, we're going to use zones and vias again. So I've switched my grid back to a little larger grid, and I'm going to draw some zones on this guy. And with that, we've connected everything on this board. As a final check, we'll want to run the DRC design rule check to make sure that everything is connected and there's no issues. So we run this design rule check and we get one unconnected item here. So we can go highlight that. And so here we can see we did miss a connection here. So we can close out of that. We can delete the markers off so we can see better and then close out of that. So we missed this guy to right there. We'll rerun the DRC. We have no unconnected items, and all of the violations on here are Silkscreen and text variables, which we will clean up next. Just as a status check, we can check out what this is going to look like in the 3D viewer. So if we go into View and we look at the 3D viewer, since I've pulled in, or KiCad already had 3D models for all of our components, we can see what this will look like in 3D. And this is a handy way to kind of check everything out, see where we're at. Obviously there's some Silkscreen to clean up, but this is what our board's going to look like. We also can go into the settings and turn off the solder mask, and then that'll let us see the copper. One more thing that I'm going to do on this board looking at this is add a zone to the back as well. That'll help with thermal. It'll help pull heat out of the regulator. So we'll go into the back copper, and we'll just make this a ground plane. To clean up the Silkscreen, I like to turn off all of the copper and then just turn on my fab layer and the Silkscreen layer. Although first we're going to clean up the fab layer because we have some reference designators that are not correct. So for some of these it has the $ref and instead it needs to be $reference, and then that will fill in correctly. Now if we rerun the design rule check for that, we've gotten rid of everything except for the Silkscreen overlap and solder mask, so we'll clean that up next. Since we're dealing with Silkscreen, I'm going to turn off my selection filter for everything except for text. One thing that's important with Silkscreen, I like to make it so it can be read either all in one direction, so it'd either be right side up here or turned 90 degrees. You don't want any Silkscreen that's upside down from one angle. KiCad does give you these little lines that indicate kind of which component the Silkscreen goes with. So if I just start clicking on these, I can pull them out, figure out which component they go to, and start placing them. I am going to go back into DRC and delete all of the previous markers so we can see a little better. right around the part, it may get a little tight, so for something like this, we can place it off to the side. And as long as we have that layer connected, we can go draw a line from it and point over to the part. And now if we go rerun our design, we'll check. We have 0 errors and 0 warnings. To ensure we'll be able to hook everything up to this, I am going to go add some text kind of describing what this design is, and then also labeling the inputs and outputs. So the last thing I wanted to add to the board is just some test points that will allow us to probe this with an oscilloscope more easily later on. So I've added these sets, so we'll have 2 ground and then V in and then 2 ground and V out. And so I'm going to place these. To add these, I just went into the schematic and added some 1x4 connectors, and these will make it pretty easy to get scope probes onto this board. So on the layout, we're just going to move these into a spot where they're accessible. I will also add some Silkscreen to identify the pins on these. And with those test points added, this board is complete and ready for fabrication. I'm going to order a few of these boards, we'll build them up, and then we can test them out and compare them to some other regulators.